Saxon's Calculus, Lesson 70, they call game playing with a function, the derivative of the function, and the double derivative of a function. So basically, they want you to look at the examples and figure out what they're doing. So in example 1 on page 348, it says, if f of x equals ax cubed plus b, obviously you need to find the a and the b, and then the graph passes through 2 and 25, and we know that the f prime of plugging in a3 gives us 81. Now, it doesn't help me much to plug in an x as a 2 and it equals 25 if I still have a b in the problem. So that is not a good starting place. However, if I derive this and I plug in 3 and it equals 81, it might help me resolve. So let's try. Yeah, they went ahead and they wrote out as far as they could get. We can do that. So let's do 25 equals 2 cubed is 8, so that's 8a plus b. And then, of course, they were stuck. So now when you derive this formula, you get 3, a is acting as a constant, x squared, and b is a constant, and it's dropping off. So now we can plug 3 in and get 3. Oh, sorry, it's plugging into the x. A equals the 81. I wrote that out of order. So this was that 3. Then the a should have been written next to follow the order, and then 3 plugged in as the squared, but it doesn't really matter. So 3 squared is 9 times 3 is 27. 81 divided by 27 tells me that a is 3. Now that I know that, I can plug in back over here and solve for b. So 8 times 3 plus b equals the 25. So let's see, b equals 1. Now we have our a and our b. Find the function of, so it basically wants the equation. Which should be x cubed with your 3 plus 1. The function is a real quadratic function whose graph, no, I feel like I'm looking at the, yes, I've jumped to example 2 and I'm going, where are they getting these boundaries of 1 and 2 and 3? Okay, yes, equals f of x. That's what I thought they were looking for. Yep, got it. Now let's look at example 2, which had me so thoroughly confused. All right, the function f is a real quadratic function, okay, whose graph passes through 2, 9, and 0, 1. And the slope of the graph is 6 when you have plugged in a 2. So 2, I'm wondering, I'll write it that way. Okay, is the slope, and then find the general equation. So we know that if it is a standard, it should look like f of x equals an ax squared plus a bx plus a c. And I may not have all those parts, but that's the standard equation. So now I can plug in the 2, 9 and the 0, 1 and see what that gives me. So 9 will equal a, 2 squared is 4, I realize that should say 4a, plus, and 2, so 2x plus an unknown c. Also, if I plug in, then 1 would equal and 0 plugged in drops it, 0 plugged in drops it, so that just equals C. I could now plug that in here as a plus 1. So I've got 4A, oh, I didn't think that felt right, 2B, because I plugged the 2 in for the X, 4A plus 2B plus 1 equals 9. Okay, that feels better. Now, the slope information was when we derived the answer should equal 6. So let's derive our original, debating which one is the best one to derive. Yeah, the original one is what my instincts were telling me. So when I derive this, I'm going to get 2 coming down with the A and a single X now, plus the B. C was a constant and drops off. So this will equal a slope of 6 when I plug in a 2. So 2 gets plugged in here. So 4A plus B equals 6. Oh, foo, hang on. I was on the right track. I just was throwing myself off. So this most definitely is 4A plus B equals 6. Originally, when I looked at this, I was expecting to have an answer for A or B, and I didn't. And that's where I thought maybe I'd made an error, but I have not, because I have this equation with an AB and this equation with an AB. So if I kind of put that in the right order, then that puts me at 4A plus 2B plus 1. Oh, and actually let's move that 1 and let's make that equals 8. So equals 8. Yes, now I can eliminate the A, the 4A statement, to solve for the B by minusing this whole entire equation, so they'll cancel off. B minus 2B is negative B equals 6 minus 8 is negative 2, so B is 2. Checking. Yes, okay. Now I know C is 1, B is 2. I didn't find A yet, but I can by throwing it back in maybe to this equation. So 4A plus 2 equals 6. 4A equals 4. A equals 1. Now I have all three. I can write my f function. So f of x equals A, which was 1, don't need it, x squared, plus B, which was 2, plus C, which was 1. Oh boy. Okay, example 3. If this is the graph of the derivative of f of the original equation, so f prime, this is the picture of f prime for the original f function. Sketch the basic form of the original function. Okay, there is a note here that if you need some help, you can reference back to page 297 and 298 as helpful. But what I need to remember in this now, unless you're looking at the book, you don't have the derived. So they have a dot here at 1 and negative 1 and a parabola. I'm just going to swoop it. So that's basically what they give you. So when we're looking to sketch the graph of the original, if we have crossing points at 1 and negative 1, we know that our slopes are 0 at 1 and negative 1, wherever those dots may be. All right, I know that much. I also know that the derivative is going up, so it should be overall my graph increasing. So if it's and up to 2 curves. So if I'm overall increasing, that's a possibility. I'm debating if my 0 dot being down into the negatives tells me anything about where it's crossing. I feel like it should be up in the positives. I feel like this should be up a bit more. Crossing maybe somewhere up here. And I definitely, oh, this swoop is in the wrong place. I definitely want a, okay, so I'm gonna move this down just a tad. I want it here, making my hump maybe something like so. And I know I need to do another swoop at this spot. So maybe something like that. Oh, I feel like that's bad. Okay, that is not a great graph. Their actual swoop looks like this. And this spot is at the 1, and this spot is at the -1. And then, oh, maybe I should just do that and draw the x-axes. Something along that line basically is what we were looking for with the 1 and the -1. Oh, I don't know why I was having such trouble there. Example 4. If f is a function such that the graph of the double prime is a straight line as shown, sketch the basic shape of the graph for the function. All right, so since double prime is forming a line, that's telling me that I actually have an inflection point. And that, let's see, where is it crossing at? Okay, I didn't give you the original. So at -1 is where they're crossing with a line, and this is for the double prime. So then on my actual sketch at -1, I will have my inflection point, wherever I wish to put it, and then I'm going to swoop because it's the inflection point. And it said a rough sketch. Alrighty, example 5. If the double prime of x equals 10, and the original derived 0 gives 2, and on the original function, if I plug in 0, I get 3, find the equation of f. Okay, so because I have a double prime that is positive, and it's just 10, that's a straight line. So you're picturing a straight line at like 10, basically. Then we know that that equation, I need to work backwards. So this would be y, I don't want it in y. I need to work it backwards by integrating it. So that is creating 10x plus c, because I don't know what other things I might have here. Although it being a straight line, I feel like that would be a 0, but I should not guess that. Then if we plug the 0 into this, we would get that c is a 2. So my instinct was wrong on that. And then if I work backwards, integrate again backwards, that's going to give us 1 plus 1 is 2. So 10 divided by, so 5x squared plus 2x plus c would be that equation. Oh, and they're calling it C2 to avoid confusion. And then we knew 0, 3, so 0, 0. So this c is now 3. So we're getting the equation. The original equation would be f of x equals 5x squared plus 2x plus 3. Yes. All right, so basically you just need to be integrating to work your way backwards. Oh, that was the last example.